Thank you. So my slot is 9 o'clock till 11 or 9? And then Mike comes on. Yeah, okay. So I'll try and keep this short. So James Webb Space Telescope +2, because it was launched on Christmas Day 2021. So it hasn't been in operation for quite that long. It obviously took a few months to get it going in the first place. It took a few months to unfold everything from the rocket, get it to the Lagrange point 2, L2, where it's now orbiting that little red dot, sitting approximately 1 million miles above midnight. So let's remind ourselves why it was put up in the first place. One is to look at the very dusty and warm environments of exoplanets. And secondly, its job was to look back in time. If we remind ourselves that the universe was born in the Big Bang, and that's us now 13.8 billion years later, the question is, how far back in time can we look to see what happened in the very early universe? In particular, we think stars and galaxies were born in that first little section between the two blue lines. And the question is, when did the first stars and the first galaxies come into being? If we expand that little section out, then we see that we're looking back to a few 100 million years, a fraction of a billion years after the Big Bang. So how far back can we go? Redshift, remember, because of the expanding universe, redshift tells us how much the light has been stretched. So it's a useful sort of yardstick, if you like. It's the thing that we can measure that tells us how far back in time we're looking. So redshift of 0 is now, 1 is quite a few billion years ago, 4 is getting back to the first billion years or so, but we would like to get back to this era. Hubble has taken us to about 500 million years after the Big Bang. We hope that we can push that further with the James Webb. Maybe one day James Webb will get us back to here 100 or 200 million years after the Big Bang. We're not quite there yet. It's only been in operation for, well, no more than 2 years. But that's the idea, to explore this part of the universe back when the first stars and the first galaxies were being born. So perhaps if you remember last year, June 2022, after it had been up there for 6 months, they'd calibrated everything, they had the first public release of images, which I told you about last Christmas. So I'm going to forget the first year and move straight on to what has it been doing in 2023. That's what this talk is. So, roughly speaking, I thought I'd pick something interesting for each of the calendar months of 2023. Back in January 2023, they released this, the zodiacal light from another star system. The zodiacal light in our solar system is all the dust that's left over once the planets have formed. So most of the planets hoovered up most of the material in the solar system, but a little bit of dust is left in the plane of the ecliptic. And we see that, if you've got very dark skies, as the zodiacal light. James Webb Space Telescope has now effectively seen the zodiacal light of another star system. In other words, we know that this particular star, which has been blanked out of the middle, otherwise it's far too bright, the star system does have a couple of planets, but this is the first time we've actually seen the dusty, because this planetary system is seen edge on, this is the dusty part of this particular planetary system. So the zodiacal light of another planetary system. This is, of course, an artist's impression, but in February of this year, it discovered an asteroid. That doesn't sound too spectacular, because an asteroid that's 100 or 200 meters in diameter is no big deal. We see them all the time going past the Earth. The difference is that James Webb saw this asteroid when it was still in the asteroid belt, a huge distance away compared to the ones that graze the Earth occasionally. So the fact that the James Webb can see an asteroid only 100 or 200 meters in diameter rather than a kilometer or 2 kilometers or 10 kilometers means that we have a chance of seeing asteroids coming from a distance. The catch is, of course, the James Webb does not spend its time surveying the sky looking for these things. We will still probably have to find them using other survey telescopes. But it gives us an idea of the sensitivity of the James Webb to see such a small object at such a huge distance. In March of 2023, it took an image of this Wolf-Rayet star. Wolf-Rayet stars are very unstable stars that seem to be ejecting an enormous amount of material. It could be that before a heavy star, a very massive star, before it goes supernova, it might go through a Wolf-Rayet phase like this. This particular star, the bright one in the middle, it's about 30 solar masses, so it is pretty huge compared to the Sun. And when we look at the nebula around it, it's a very sort of knotty affair. We deduce that this particular star has been episodically throwing out a whole load of matter for probably many, many thousands of years. It's been ejecting lots of material into the interstellar medium and generating this nebula around it. It's been calculated that this particular star has probably lost the equivalent of 10 solar masses simply from the outer part of the star being blown off to create this huge nebula around the star. So given that we think this is, in a sense, a prequel to a supernova, these sort of stars are being watched very carefully to see how they are behaving. In April 2023, it imaged the planet Uranus. Voyager, back in 1986, went past Uranus. If you remember, it had a spectacular visit of Jupiter and Saturn, got as far as Uranus, and it was really boring because it saw essentially nothing. It looked at the planet, it appeared to be blank. That didn't bode well, but it did go on to look at Neptune, which was a little more interesting. But now the James Webb has gone back to Uranus, and we get the ring system showing up beautifully, but also we get a little bit of surface detail that Voyager didn't see. Even though, of course, Voyager is so much closer to the planet than the James Webb is, we still see a little detail. There appears to be one of the poles. When that pole points towards the Sun, it seems to change color, which is quite interesting. So they're trying to work out what's going on there. And this very bright spot on the left-hand side seems to be part of a storm system. So in other words, Voyager was very unlucky. When it went past this planet, there were no storm systems on the planet, and therefore it looked almost blank. But now it's starting to look a little more lively. So James Webb is not going to be spending all of its time looking at the planets, but every once in a while it's going to put its gaze back to the outer planets to see what's going on, and it might pick up a lot more information about Uranus than we knew from the Voyager space probes. Astronomy picture of the day from May of this year shows the star system formula. Again, the star itself has been blanked out because it is so bright, but the rather warm, dusty environment of this very early proto-planet system is warm enough that the James Webb is picking it up very nicely, and it looks like for the first time we've been able to image detail within the disk of a star that's developing a planetary system, such that you can identify, if you want to draw an analogy to our solar system, it looks like it's identified the equivalent of a Kuiper belt out a large distance from the star, and then there appears to be a bit of a gap, and then another belt which might or might not be similar to our asteroid belt, and then there's a disk of planets forming within that. So we get an idea of the entire structure of the solar system. It is possible to image individual planets, but it is a very dusty environment, so you really do need an infrared telescope to tell you what's actually going on. And the fact that we can distinguish different sections of this disk rather than just a flat pancake, we can see structure, and so by observing systems like this, we can start to see how planetary systems develop around other stars. Astronomy picture of the day from June of this year shows Pandora's cluster. Part of this cluster has been imaged previously by the Hubble, but now with the James Webb's larger mirror, it has a larger sensitivity, it can take images in a shorter time. So this is a mosaic covering a relatively large chunk of sky, considering the size of the chips aboard. A large chunk of sky, a mosaic, and it only took a few hours of imaging, which would have taken a lot longer if we had had a smaller mirror on the James Webb Space Telescope. So the objects in this image, we have a number of stars, but we have a huge number of galaxies in this particular cluster, Pandora's cluster of galaxies. The first estimate is that the total number of stars and galaxies in this image is perhaps 50,000. So that's going to keep PhD students going for quite a while. We've got images like this, and it's taking spectra of a lot of those close and a lot of those distant galaxies. And so by taking images like this, which have got a huge amount of information in them, we're going to understand better galaxies, galaxy clusters, dark matter, and very distant galaxies that have been imaged because of the gravitational lensing, this distortion that we can see on these very distant galaxies. In July of 2023, this was the first anniversary of the science releases. Remember, it took 6 months to get everything calibrated and working, so it was the middle of 2022 when it started science operations. So by the middle of 2023, it was its first birthday, and at that point, they released the first birthday picture. It was from the Rho-Ophiuchi Molecular Cloud Complex, a very interesting looking image, and you look at it and think, what the hell is going on there? There's red, which is a whole load of hydrogen that's being blasted out of some very young stars. This is a star-forming region. It's actually the closest star-forming region to us. This is only 400 light years away, which is effectively on our doorstep. And there's a whole load of hydrogen coming out of these stars, and this huge cloud here is being excavated by the solar winds coming from a very massive star that's embedded right in the middle. Given that Rho-Ophiuchi is a well-known target for amateur astronomers, I did wonder where this particular part of the Rho-Ophiuchi complex was, because none of those stars are actually Rho-Ophiuchi. So I went back to an image I took a long time ago and said, well, that's the Rho-Ophiuchi cloud complex. Some Rho-Ophiuchi is actually that star there, and then there's Antares and M4 and other things. So I thought, where in there did James Webb actually take its image? Took me a long time to figure out if we look in there and blow it up, that's still not enough. It's actually in the middle of that. If we look in there and blow it up, that little yellow splodge, that's 1 pixel for me, but that's the entire image for the James Webb Space Telescope. It's a reminder that if you're using a camera with a short telephoto lens, well, the James Webb focal length is a bit longer than that, yeah? I used a 135 millimeter lens. The focal length of the James Webb is 135 meters, not 135 millimeters, so no surprise it's 1,000 times the magnification, as it were. But it was interesting that you can actually identify the splodge that James Webb took for its anniversary picture. And that's effectively where we're going, from that pixel there to the entire image that we were just looking at. In August of 2023, James Webb imaged the supernova that went off in 1987 in the Magellanic Cloud. And it's very interesting to note how things have changed, because Hubble has been observing this for quite a few years, and in a sense, the James Webb is now taking over. And what they've determined is that the supernova right at the core, where the star has now basically blown itself to pieces, but we're getting some very interesting structures starting to show up. For those not familiar with this, these odd things here are just the stars with diffraction spikes that produce some odd-looking results. But we're looking at that ring, what looks like a sort of pearl necklace around there. They deduce that supernova, just like the Wolf-Rayet star we saw moments ago, supernova are often very stable. Because they're very heavy stars, they are very unstable as they come to the end of their lives. And this particular star has probably for thousands of years been blowing off the outer atmosphere of the star into interstellar space. So when a supernova does go off, it's not a big bang in a vacuum, it's basically a huge explosion inside something which is already filled with the debris from previous material being spewed out by the supernova. So what happens is the shock wave from the supernova goes tearing through all the material that's been expelled for the last 10,000 years or so. And what we're seeing here is the shock wave hitting the material that was expelled thousands of years earlier. So by looking in detail at what's going on, we get a much better idea of the dynamics of how supernova actually go off. In September 2023, another astronomy picture of the day. Right in the middle here, a star is being born. This is a very young star. We're used to the idea of some stars living for trillions of years. Our sun will last for billions of years. Even very massive stars will live for millions of years. This star is probably only thousands of years old. It is very, very much in its infancy. Something is being born right in the middle of that very dusty environment there. And as material is collapsing in to make this new star, this protostar, jets are coming out. And these jets are again coming out of the star into the interstellar medium, and they slam into the interstellar medium and produce shock waves of their own. This is, we think, part of the normal process by which stars are being born. But if we can see it in this much detail, then again, if James Webb looks at lots of these stars being born, we can get a much better idea of how stars go from a large collapsing cloud to actual stars that we understand today. It's interesting to note that the jets themselves have been studied in some detail, and because of the nature of the jets not being very smooth, but apparently being rather twisted when you look at them in more detail, they've determined, or at least there's a very high probability that what's being born right in the middle is actually a binary star. And as far as we know, we've never seen the birth of a binary star before. So James Webb will be keeping an eye on this in years to come and looking for other examples to give us better ideas of how stars are born. That was September. In October, another very interesting event, a so-called kilonova. That's the kilonova, that rather boring-looking red dot on the extreme side there, on the extreme left. A kilonova is what happens when two neutron stars collide with each other. It was seen as a gamma ray burst. It was also detected because of the gravitational waves that were produced by two very massive, very compact objects crashing into each other. It's interesting for a number of different reasons. One is it's separated from its host galaxy because that is the galaxy it belonged to. So it's thought that when these neutron stars were born, probably in a supernova explosion in the first place, they were actually given such a huge kick when they were born that they were actually ejected from the galaxy. And they've spent the last million years or so traveling out of the galaxy to this point here, at which point the two neutron stars themselves collided to produce the light that we see as a gamma ray and the gravitational waves which were seen by the gravitational wave observatories. But one reason it's very interesting is not only the fact that this was one of the brightest gamma ray bursts ever seen, it currently holds the record as the second brightest gamma ray burst of all time. When the James Webb looked at the spectrum of this particular little red dot, it found the telltale traces of heavy elements. And in particular, it found the element tellurium. Tellurium is element number 52. It's way heavier than iron. It's way heavier than copper. It's heavier than silver. It is one of the heavy elements that previously we thought must have been made in a supernova explosion. But no, it appears that colliding neutron stars can generate heavy elements themselves. So the direct evidence that we see these heavy elements is evidence that the heavy elements that we see in the periodic table here on Earth were made not necessarily in a supernova, but perhaps in colliding neutron stars. Also in October 2023, the James Webb Space Telescope imaged the familiar Crab Nebula. It looks, at first sight, perhaps similar to the image produced by the Hubble Space Telescope, but what's interesting is the fact that if we flash back and forth between them, we notice that the James Webb Space Telescope image is 20 years after the Hubble image. The nebula has changed. Yes, we're looking at it in the infrared. If we compare with the Hubble, slightly different color, slightly different elements being imaged because we're looking in the visible rather than in the infrared. But if I switch backwards and forwards and you look, for instance, in this corner or in that corner, if I go backwards and forwards, can you see the difference in size? The stars are perfectly lined up, so we know we've got the magnification correct. But basically, the James Webb image looks larger than the Hubble image because it is. This particular supernova remnant has expanded in the 20 years between the Hubble image and the James Webb image. So we can actually gauge how fast all of this is expanding, as well as take a spectrum and work out which particular elements are present. We're interested in how much of that is iron, how much of that is nickel, because it tells us something about how the supernova went off that generated the nebula that we can see. Also notice all this milky stuff around the edge that looks rather weird. This is the result of electrons bending in a magnetic field and producing what is called synchrotron radiation. It's a particular type of radiation that happens when charged particles move in magnetic fields. You get the hint of these magnetic fields by these sort of little traces and little arcs and little lines, in effect a bit like the elements in the solar corona. By looking at the features in this nebula, we can start to trace out the magnetic field which is generated by the neutron star at the center of the nebula. And the synchrotron radiation here allows us to sort of see where all of these charged particles exist. But being able to see the change in size, I think, is quite interesting to show that it's a few % bigger than it was when Hubble looked at it a couple of decades ago. Remember, this one went off about 1054, that when the original supernova was observed. So 20 years is actually a few percent of the 1,000 years it's been since this supernova went off. The final one, because I haven't got one for this month, the final one is the astronomy picture of the day for November. So this is a month or so ago. This is, again, a not very spectacular image of a very distant galaxy. But here the James Webb Space Telescope data is also mated up and married to data from Chandra, which is telling us about the X-rays that are being generated. And although it doesn't look very bright in the James Webb, it's definitely a galaxy, but in Chandra it says it's a huge X-ray source. So there's a small, very distant galaxy which is generating a huge number of X-rays, and by looking at the galaxy we can look at its redshift, and it turns out to have a huge redshift of z equals 10. That puts it way back on that line I was showing earlier. So this is very early in the universe. This is in the first few 100 million years, the first fraction of a billion years after the Big Bang. So that tells us a very big, very massive black hole generating a huge amount of energy existed even very early in the universe. Even only a few 100 million years after the Big Bang, that was soon enough for very large black holes to exist. So this is starting to pin down the argument of people who say, well, chicken and egg, did galaxies form, did stars form and galaxies form, and eventually a few black holes exist and then they start to coalesce into big black holes? No, it looks like supermassive black holes have existed right from almost from the starting pistol of the Big Bang. So the next challenge for astrophysicists is to explain how you get something so big, so massive, so early in the universe. So that's really stretching the theorists. So I've given you a whistle-stop tour of what the James Webb Space Telescope has been doing for the last 12 months. I hope you all have a wonderful Merry Christmas. Thank you very much.